We're done with the first two chapters. Today we move to the third chapter, which is about coordinate systems. Lastly, third chapter is about coordinate systems. Skip chapter 3 for now. We'll discuss chapter 4. Okay? We'll skip chapter 3 for now and we'll discuss chapter 4, which is orbits in 3 dimensions. Alright, let's look at this. Before we start discussing the orbits in 3 dimensions, we'll take a look at something called geocentric right accession and declination frame. By now, you should understand what a reference frame is. Okay? A reference frame is a measurement system, or where you start trying to figure out where a particular object or what is the orientation of a particular object in space. Right? So if you look at this, Earth is here. This is Earth. Okay? This circle is representative of the Earth. What you see in this grid lines, the sphere in the grid lines, is called a celestial sphere. So everything we see in space, we see in that celestial sphere. How do you uniquely define the position of a celestial object? Latitude, longitude. Latitude, longitude will define what? Will define a position on Earth, right? The surface of Earth. What is latitude?
Oh, it's hard. It's like horizontal.
Latitude is? What is it? It's a? It's an angle essentially. Mathematically, it's an angle, right? Latitude is an angle. How do you represent latitude?
Horizontal.
Degree.
Huh? So many degree, north or south. Don't you say that? How do you represent the position of a particular place? You'll say so many degree north or south and so many degree east or west. North or south of what?
The equator.
The equator. Right? So longitudes are
lines which run from north to south but are measured from east to west. Latitudes are lines which run from east to west but are measured north to south. Make sense? So this right accession and declination frame is very similar to latitude longitude. So how do you measure the longitude? Where do you measure the longitude from? Huh? What is the 0 degree longitude?
Equator. The equator. Oh, you know, it's fine.
The equator is what? 0 degree? It's latitude. 0 degree latitude.
Onto the pole. At the middle. Atlantic Ocean.
Huh? So north to south pole you can go anywhere, right? It can go to US, it can go through India, you can go through many other countries, right? So what is that 0 degree longitude?
England.
It's actually England. You understand what GMT is?
Yeah.
What is GMT? Greenwich Mean Time. Greenwich is a place in UK. The 0 degree longitude runs from North Pole to South Pole through Greenwich. Okay, so that is the reason on the left of that Greenwich, everything is west. On the right of that Greenwich, everything is east, is considered east, right? So that 0 degree longitude is.
And where does that run from the other side of the earth?
I'll tell you that.
Because I want to say everything.
Right. If it's with respect to Earth, it doesn't change, right? The longitude, 0 degree longitude doesn't change. It's always running through Greenwich. Even if Earth is rotating, it's running through Greenwich. If Earth is rotating, every other place on Earth is rotating, right? It's not like Greenwich is rotating and some other place is just staying. But when we define this, so that is the 0 degree longitude, and going east is 0, 1, 2, 3, whatever degree longitude. You can do 0 degree longitude, so you have 180 degree east, 180 degree west. Get it? What is a 0 degree latitude? The equator. So you have 0 degree north and 180 degree north, and we actually have 90 degree north, 90 degree south. You don't have 180 degree, right? So it's just this. You don't do this. That doesn't make sense.
You don't do what?
Latitude, you have, what is this?
Latitude.
0 degree latitude. What is this? 90 degree north latitude. Right? That is the pole. Then you have 90 degree south latitude. Right? How about longitude? So longitude you measure. So you have this is the 0 degree longitude. Okay. So you have 180 degree and another 180 degree. You get it? So what we do is, that is with respect to Earth. Now when we do this for anything in space or anything in the universe, we define this direction. This is the Aries direction, okay, the Aries sign. Right? This is the vernal equinox. This is defined as the 0 degree. So you see this, you can see that this longitude is right accession, right? So you have 0, it's measured right accession. You see?
Say it again.
It's
So-
right ascension.
Almost as if like
So if you go from this, what is this direction? This direction is north. Okay. So you go from north pole to south pole, going through Greenwich, would be 0 degree longitude. So you have right ascension. You're ascending from in the right sense. East is right of that.
What are you referring to?
I'm just referring to longitude. So right accession is nothing but longitude. Why is it right ascension?
Wow.
Because it is measured in the right sense. If this is north, it's measured in the right sense.
So it gets bigger
What is
going to the right.
Right.
Okay, so yeah, alright.
What is ascension?
Ascend. Ascension is ascend. Ascend is increase. Ascension is increasing. So from in the right, increases in the right sense. So here what we have as right ascension is, Louis,
No, I asked a question.
you asked it? Somebody asked it for you?
I was going to say the optional dissension is what?
Ascension.
Yeah.
Ascension.
Yeah, that's why I said never mind.
Yeah, ascension is nothing but ascending.
Alright.
So when you have nodes, we talked about, we did not talk about nodes, we talked about nodes. So you see, this is ascending in the sense, it is ascending in the right sense. You see, it's increasing, right? And then it comes to 360 degrees. It's ascending in the right sense. This, what you're seeing, is a celestial sphere. The hatched lines or the hatched sphere is a celestial sphere. So everything you can see is a sphere in space.
So you said the 0 point is in the UK. For every planet in the solar system, we've chosen a 0 point for that. Right?
What we're doing is, since we are on Earth, we are always, this frame, the right accession, right, it says geocentric, right? Geocentric means this frame is centered in geo, which is Earth. Okay? This is with respect to Earth. This frame is with respect to Earth. If we had a right ascension and right declination frame on Sun, what would it be? It would be a heliocentric right accession declination frame, right? So since we are on Earth, it's easier for us to visualize everything from Earth. So this is with respect to Earth.
So we don't ever use.
We do use frames on other planets, other bodies, but only when it is necessary, right? If you want to figure out the distance from Moon, then of course.
So like, let's say we're launching the rover to Mars.
Mm-hmm.
We know where the 0 point on Mars is. We can tell you this is where the rover is located.
Right. So we may not know, we have mapped actually Mars and Moon very well. So we know where that zero would be.
Mm-hmm.
Right? The zero line will be. So we can say, yeah.
But gamma, where is gamma?
That's not gamma, that is the Aries sign. That is the horns of
Aries.
Aries. Okay. So
The
that
star, the star constellation?
is, it's the constellation. Aries is that, what is it? It's a,
Mars.
the symbol of Aries is a ram, right? Ram has those horns. So the Aries constellation is in the shape of horns of a ram. So that is the reason that sign is there. Okay. So that Aries constellation is defined as the 0 degree longitude or 0 degree. Okay. And what is that? How is that that direction defined? We have already discussed this once. From the center, on the first day of spring, okay, the line passing through the center of Earth and the Aries constellation is that direction. Is it? Can it be uniquely defined?
Can you say that one more time?
The first day of spring, the line passing through the center and 0 degree longitude or meridian is the Aries direction. That's where the constellation used to be. Now it has changed a little bit. It has moved. But if you look at the line from the center, you passed it through the 0 degree longitude on the first day of spring. It passed through the Aries constellation. Does that make sense? So Earth is constantly rotating, right? But on the first day of spring, it is always at a particular orientation, always. It comes back to that orientation and position. So this is defined with respect to that, okay?
And so we know if we define that direction on the first day of spring, we can keep a track of how that position is changing, how that relative position is changing, right? So we know with respect to Earth where something is, all right? So that is the 0 degree right recession, okay? And of course, you have declination. Declination is nothing but latitude, okay? And this, the equatorial frame or equatorial plane is defined as the 0 degree declination. Now, with respect to this, can you always define where a celestial body is
Yes.
in that sphere?
Well, I guess it covers all the directions. Right?
Huh?
I mean, it covers all the directions that you could observe that body, so I would think.
Right, so anywhere on the celestial sphere, right, wherever that celestial body is, you can say it is this much degrees right ascension and this much degree declination. You just need to know the distance. So on that same line there could be two objects at different distances, but their relative position is the same. You see it?
Well, actually, I was just stupid. About how many? No, that's stupid. I thought I asked how many miles between each degree that changes as you go up.
Yes. So sphere is like a spherical coordinate system. How many? We study Cartesian coordinate system. We study cylindrical coordinate system, and then spherical coordinate system. So how do you define something in a Cartesian coordinate system? All are distances, right? How do you define something in a cylindrical coordinate system? There are two distances and one angle, right? How do you define something in a spherical coordinate system?
3 degrees.
Two degrees and one distance, right? So that is the spherical coordinate system. You see that? It's just two angles. Two angles are right ascension and declination, and then you go how much ever distance you want in that direction, that line. And so that will uniquely give you the position of a celestial body. Okay?
You said the equatorial plane was at 0 degrees latitude?
0 degree declination. So we are moving from latitude, longitude is restricted to places on the surface of Earth. When we talk about something on a celestial sphere is just observing everything in the context of a sphere. The moon is in that celestial sphere. The sun is in that celestial sphere. Every planet, everything in our universe, everything observable in our universe can be observed in that celestial sphere. Right? You see that?
Are you saying inclination?
Declination. Declination. Okay. So once you have defined this frame, how is this frame relevant to what we are trying to study? Right? We looked at orbits, correct? So the first thing we looked at was, you remember what this equation is?
Acceleration.
What is this equation? This is a problem, two-body problem statement. You should always remember this. Okay? So if you wanted to define uniquely something, see, this R is a vector. Okay? Look at this as a differential equation. And what is the order of this differential equation?
Second one.
It's a second order differential equation. Why is it a second order differential equation? R double dot, right? Double derivative. But also think about R is what? A vector. So in reality, this is a sixth order differential equation. So you have R
Rx, Ry, Rz. There will be 3 first order differential equations. That will be the 6th order system, right? So if you want to solve for this, how do you solve for this? How do you solve for integration problem? How would you typically solve for this? If you integrate this twice, you're going to get a value for R, right? But what you'll end up with is 6 constants. This is, if it's a finite integral, if it's an infinite integral, you end up with 6 constants. You need 6 constants to uniquely define the solution to this problem. Okay? So what we do is, accordingly, we need 6 parameters to uniquely define an orbit. This is actually a solution to this problem, is a solution to the orbit. You understand? This is the 2-body problem. This defines the motion. What is an orbit? Orbit is essentially the trajectory of the body, this orbiting body around a central body. It's a trajectory, it's a path. So if you want to define the orbit, the solution to this problem will give you the position of the orbiting body. Got it? And what do we need? We need 6 elements or 6 constants to uniquely define the solution. Accordingly, we can say that there are 6 elements which uniquely define an orbit. You need 6 parameters. Those are called orbital parameters. You've heard about orbital parameters? Not come across anything like that before? So what are those orbital parameters? So what we do is, to define those orbital parameters, so you think about this. This vernal equinox is very well defined, right? The celestial equator is defined, the right ascension, declination, and this is the satellite. So if you want to understand where the satellite is, you see where the satellite is? So this is the satellite, and you want to understand the position of that satellite. How do you define the position of that satellite? 2 angles and 1 distance.
Wait, so did you say that when you're on Earth to find a location, it's still 2 angles and
2 angles and 1 distance in that direction.
So 2 angles and a distance going up to like altitude?
Altitude.
Okay.
Altitude, or we say the position vector.
Okay.
So this need not be a vector. This R, if it's a vector, it uniquely defines anyways. If we do a right ascension and declination and do a distance, that will also give you the vector itself. Okay? So you should understand this. See, this is the most, if you look at it, this is the most intuitive way of saying where the orbiting body is. Any orbiting body with respect to Earth. Right? What is the instrument you can use to measure? What is the one instrument you're going to, if you're asked to figure out where the position of a particular object is in sky, how are you going to go about doing that?
A sextant?
Huh?
A sextant?
People understand sextant here?
I just know it's like a little tool you use to look at the horizon. I never really used one.
So what you're going to use is, you're going to use an optical device which will. So what you're going to do is you're going to mount an optical device, okay, and you're going to first align it in some direction, and then what are you going to do? You're going to do this and this, and this precisely you're going to measure what this angle is, and then you're going to do what this angle is, and then what you're going to do is through some optical physics you're going to measure. You're going to, let's say, shoot a radar. Have you heard about moon bouncing? Right? How do you figure out the distance for moon, for example?
You can shoot some type of signal over there and then see how long it takes to get back.
Yeah. So that you use a radar, right, to figure out. You cannot do that for more something which is outside of our universe, because it takes light years for it to come back. So we don't do that for something like that. But there are other methods. But what you're going to do is you're just going to fire something and come back. So that is the basic understanding of those two angles are very important. You understand? Once you figure those two angles, you can say this is the position vector of my orbiting body.
What is the zero for determining the third value? Is it sea level or is it the core?
It's the core.
Okay.
It's always the core. So what we assume is, again, have to go back to assumptions. What did we assume? Earth is a spherically homogeneous body, which means every place on the surface of Earth is equidistant from the core. Right? We just add that to the distance, this distance.
Okay.
Got it?
So which one of those three were you just saying?
So this is how you see R is a position vector, right? If you want to figure out that position vector, if you want to really, what you need is, you can never really measure the position vector. Can you measure the position vector? How do you measure the position vector? So for example, if I give you, measure the position vector of this in this frame, what are you going to do?
Need a origin.
Huh?
Need an origin.
That's the origin, yeah. So you're going to do something like, measure this, and yeah, you're going to do that, right? In this one, can you do that with moon? Can you do, let me do that, let me do this, let me do this?
Not really.
So what you do is you do angles. Angles you can do, right? And this distance is, you just bounce something off this distance. Got it?
That's what we did with propulsion class.
You see it? So you cannot bounce something off where there is nothing. You cannot measure this distance, you cannot bounce something off because there is nothing here. There is nothing here. There is nothing here. Right? But if you think about this, you can measure this angle and this angle, and then you bounce something off this. And you know this distance. Got it? Then that is how you get this. Okay, this delta is the declination, okay, and alpha is the right ascension. So, as for exam point of view, what you'll be given is, you'll be given a position vector and asked to find the right declination, right ascension and declination of that orbiting object. See, practically speaking, position vector does not make as much sense, as much intuitive sense as right ascension and declination. Right? If I give you the position vector of some place on Earth, does it right away hit you where that place is? If I give you the latitude, longitude, will it hit you where it is? It will immediately register in your mind, right? So that is what we are trying to do. Okay? Alright.
let's do this orbital elements. Okay, and for this, let me take you to this. Now this is very important. Please pay attention. By far, this is the most important thing you are going to learn as part of this course. If you don't want to take anything with you, please take this, what I am going to discuss now. Orbital elements, huh? This one? No. It's recording.
I don't want to record it.
So you can just look at the, I'll just send you that slide. Okay? You want to turn this?
I mean,
So he's going to show us something.
It's going to just look at the constant thing. So
So the thing that you said that's the most important is not what you just covered. There's nothing to do with that.
it has something to see. Everything is a build-up. It's not disconnected.
Okay.
But this is what you should take. Okay. Okay. So what I told you is 6 parameters are required to uniquely define the orbit. Alright. Now what you're seeing here is you're seeing Earth. Okay, this is Earth. There are 2 frames here. One is it's called the ECI frame or Earth Centered Inertial Frame. So we have Earth Centered Inertial. This is one frame, okay? And this is how we define this frame. This frame is attached to the center of Earth, but it doesn't rotate with Earth. That makes sense? This frame is attached to Earth, but it doesn't rotate with respect to Earth.
So what's it rotating?
It doesn't rotate.
It doesn't rotate.
Yeah.
Does it measure how much it is? Is it the frame that helps it measure how much it's rotating? Is it like
Yes.
a reference point?
Yes.
Yeah.
Okay.
Right.
It's what?
It helps you measure. So that is what it is exactly doing.
Helps you measure what?
Helps you measure where something is orbiting or where. It also helps you measure. It's like, if Earth is orbiting, if something is orbiting at the pace of Earth, geocentric, geostationary orbits, you can always say where a particular place is. So in this frame, you can always say how Earth is rotating.
It helps to measure what?
Measure, I'll tell you. You just think about what is a frame. A frame is, a coordinate frame is what? It's a measurement system for measuring the position and orientation. Position and orientation are always measured with respect to a reference frame. Otherwise, you cannot measure position. Okay, it's a measurement system for measuring position and orientation of an object. Alright. So this, we need to uniquely define a reference frame, or to define a reference frame, you need 2 directions, okay, always. At least 2 directions. Okay. So these 2 directions, the first direction is this, again, we go back to this vernal equinox. You know what an equinox is? What is vernal equinox?
Oh, like that's
Vernal equinox is actually the first day of spring. So there are 2 equinoxes and 2
It's 2 equinoxes and 2
solstice.
summer solstice and winter solstice.
There is autumnal equinox, there is vernal equinox, there is summer solstice and winter solstice. So what is the equinox? Equinox is when the day and night are the same. The length of the day and night are the same. What is solstice? Summer solstice, the day is the longest, and winter solstice, the night is the longest. So if you look at the Earth is tilted, right? So summer solstice, the angle is like this. Your sun is like this, right? The angle is like this. So a big part of Earth is actually facing the Earth. It is always rotating about that axis, right? It goes on the other side. Only a small portion of it is facing sun. That is when the winter solstice happens. This is when the summer solstice happens. When it is here, equal parts, both north and south part are equally facing the sun. That is the equinox. When it is here, it's again another equinox. So vernal equinox is the first day of spring. Equinox is equal length of day and night. Okay.
So there's a winter and summer equinox,
Solstice.
Summer solstice, winter solstice.
and then
Vernal equinox, autumnal equinox. September 23rd was autumnal equinox.
When the world was supposed to end, but it didn't end.
There is vernal equinox autumnal equinox every year.
Yeah, but I believe it said it's supposed to end. That it didn't happen.
Alright, so let's define this. So this is vernal equinox is the direction, again it's just on the first day of spring, the line passing from the center to the 0 degree longitude.
is autumnal equinox and spring equinox.
Vernal equinox.
What is it?
Vernal. V-E-R-N-A-L. Vernal equinox.
You said that's the first day of spring.
That's the first day of spring. Okay.
It doesn't that mean when on that day the sun sets directly west? You know how like the sun kind of drifts west to like southwest and then it goes like that. Not sure.
Alright, so this x direction is defined as the direction, x direction is the direction of vernal equinox. Or on the first day of spring, when the line passing through the center of Earth and 0 degree longitude is the x direction of this ECI frame. Okay? Clear? Again, it is just nothing but 0 degree longitude.
So the x direction is the vernal.
0 degree longitude on first day of spring. Because you should realize that it's changing, right? This 0 degree longitude is changing. It's changing with respect to the day of spring. On what day of the year you're talking about.
So that why we have a leap year?
Huh?
Is that why we have a leap year?
A leap year is something else.
Okay.
So the x direction is the vernal. What's the fourth one?
Huh?
What's the direction of the fourth one? Equinox.
Autumnal equinox?
Yeah.
It's not a direction, it's the day of spring, but the line passing through the center of Earth and the 0 degree longitude through the equatorial frame on the first day of spring is the x direction. Okay? The z direction is the line passing through the center and north pole. Z. It's not zenith, it's z. Okay? It's not z. Alright. And y just happens to complete the right-handed. Y is z cross x.
You said z passes through what?
Center and north pole.
Oh,
So the axis of rotation. Okay? Now, if you look at this rectangular plane is the equatorial plane. Okay? It's a representation of the equatorial plane. Everybody is understanding, following what I'm saying?
Yes.
Or you're lost?
Can you say the last part again?
The rectangular or circular plane is the equatorial plane. Equatorial plane.
Can you show me?
This one.
Oh, you no. Oh, that.
Yeah, that plane is the equatorial plane. You see it? Wake your friends up. Wake this guy.
Yeah, he's right.
He's writing? Okay. How about that guy?
What's up now?
He's up now? Huh? You're not asleep?
No, not that time.
Alright. So you have to see here, and because this is, if you want to be spacecraft engineer, if you want to start somewhere as spacecraft engineer, at least understand this. Okay? This is a very visual understanding of what space is. This is the equatorial plane. You understand equatorial plane? Everybody understands equatorial plane? Equatorial plane doesn't end. It doesn't necessarily have to end. It can just go on. Okay?
It's called what plane? Equatorial. Where to say that?
We just know, it doesn't say.
Oh, here it goes. It says it right here on Omega. Omega substrate down there. Earth equatorial.
Equatorial plane, everybody understand? It's a plane. And this thing, what you're seeing is the orbital plane. Okay? It's sometimes called the ecliptic plane.
Which one is the ecliptic?
You see that green hatched plane? That is the ecliptic or the
Equatorial.
No.
orbital plane. Equatorial plane is what? Understand the word equatorial plane. Huh?
0 degrees of declination.
0 degree declination. So this 0 degree, you should not say 0 degree declination because it's a plane. You're right in some sense, but it's the plane. Okay, 0 degree, there one is angle, one is plane. You understand? Plane, equatorial plane, right? Equatorial plane is from where the 0 degree, the declination is measured. Okay? So, yes?
Zoom in at all to the bottom.
Better?
Yeah, I just want to see the green colors.
Better?
Yes.
Okay. So what you have is this equatorial plane, it starts at two planes. Okay? The equatorial plane and the orbital plane.
I'm sorry, I'm a little stuck on what declination is.
Declination is an angle. We'll talk about declination, not right now. Just focus on this one for now. Okay? So you see the two planes, everybody is clear with two planes, right? Where do two planes meet?
At a line.
At a line. Just like two lines meet at a point, two planes always meet at a line. So that line is this line of nodes. The line of nodes you're seeing is the line where the two planes meet.
Okay. So there's an equatorial plane and then there's a pedigree plane, right? That's that pedigree, the green stuff. That's what we call that.
Listen to me.
Listen.
Did I say pedigree?
I'm reading from right here. To
You are not listening to me then.
Alright.
So you have to listen. Orbital plane. Orbital plane. Everybody's clear? Am I clear? Orbital plane. Or ecliptic plane. Is it clear? Everybody's. Forget about. Don't confuse. Don't read that right now. Don't. It will just confuse you. So we are only talking about two planes. Equatorial plane and orbital plane. Everybody understands that? Two planes meet at a line. Everybody understands that? That line is called the line of nodes.
Nodes.
Nodes. Okay? Now this line of nodes, there is an ascending, a line will have this plane, this point is called ascending node. You have to understand this, that the direction of the motion of whatever body we are talking about is this. The direction of motion, okay, is, if you're looking from the north pole, it is anti-clockwise. Direction of motion of the orbiting body is anti-clockwise.
Okay, so this node becomes ascending node because from that point forwards, the orbiting body is going above the equator, ascending from the equator. You see it?
Yeah, I see.
You see it?
One more time, please.
See, this line of nodes has two nodes. Okay, there's an ascending node and a descending node, right? This is ascending node because from this you consider what the motion of the orbiting body. From that point forward, it is ascending. It is going above the equator. It is climbing up the equator, equatorial plane. Make sense? And there's another point opposite here, which is called the descending node. From that point forward, it is going below the equator.
What's the second word you're saying? Ascending, descending, what?
Node.
Node.
Node. N-O-D-E.
Node.
Yeah. Ascending node, descending node. Is it clear?
Where is it ascending underneath the square one?
Descending is see this point, specifically this point
It's ascending.
is ascending. You understand why that is ascending? Huh? You don't? So look at this. Here, from this point forward, in what direction is the orbiting body moving? Isn't it going above the equator?
Yes.
That point, it is ascending, it is climbing up the equator. Right? So that similar to that, there will be another node on the other side.
On the other side of the earth.
Other side of the earth. Orbits are around earth, right? On the other side there will be another node. From that point forward it is going below the equator, equatorial plane. That is the reason it is called the descending node. Make sense?
Yes.
Okay. So the angle, this angle which is measured in the equatorial plane is called the right ascension of ascending node. It all makes sense. Right ascension, is it right-handed sense? It is right ascension. It's right-handed sense. It's ascension. It's measured in the ascension sense. We talked about ascension, right ascension and declination, right? Of the ascending node. So it is measured from that x direction up to the ascending node.
What's it called?
R-A-A-N. The short form is R-A-A-N. This angle. RAN. RAN is right ascension of ascending node. You'll find this in your textbooks as well. Okay?
Okay, I hear what you're saying, but I don't see it on the picture, which you just explained.
So this cap omega is the first parameter which defines the orbits.
No, I'm still on ascending and descending. I don't see it on the picture, but I understand.
Look at this point.
Going behind.
This point. Okay? Moving forward, this is the orbit. The green thing is the orbit. Moving forward, you're climbing up the equator. You're going up on the equatorial plane. With respect to the equatorial plane, you're going up.
You're saying that the plane is the equator?
That plane is the equatorial plane. This plane.
So where's the equator?
That line.
Equator is this line.
Okay.
This plane is the equatorial plane. This plane, the square plane, is the equatorial plane. Equatorial plane is nothing but passing through the equator.
Okay.
So moving from this point forward, it's ascending. Right? Think about this point. Okay?
Okay. I see. Okay.
It's going up. You see it?
Yeah, I see.
So the angle, this angle is called this angle cap omega. It's called the right ascension of ascending node. And everything makes sense. It's measured in the right ascension sense, and it is the angle from x direction. Okay, we define the x direction and up to the ascending node. It's measured in the equatorial plane. But the second angle is this small omega. Okay, the small omega is measured from the right this line of node or the ascension, right ascending node to the perigee direction. What is perigee direction? Did we talk about perigee?
No, can I guess, bro?
It's like the bottom of the word.
Is it where it crosses over the y-axis?
Hmm?
Is it where it crosses over the y-axis? Okay, maybe it was.
Perigee direction, how did we define perigee or periapsis?
Oh, what's
Try. Periapsis, what is periapsis?
The shortest distance from the focus to the.
Yes. It is the periapsis is the point of closest approach. Okay? Perigee direction or periapsis direction is the line joining the center and that point.
Is what again?
The line of closest approach.
No, not that part. The second part you said.
The line, the periapsis. Periapsis and perigee. What is the difference between periapsis and perigee?
Okay. G is the line. Yeah, is the point. That's it.
Is it one of them is like Earth?
Yes. So perigee. Whenever that G comes in, G is for geo. Periapsis is a general thing for any two bodies. Perigee is, what is it for sun? It will be a perihee or perihelion. Okay? If this center was Earth, sun, it would be perihelion. Periapsis would be a generic thing for any two bodies. Okay? So this perigee direction is the line joining the center and the periapsis. The second angle is called argument of periapsis. Alright, let's do this. I will send you this figure. Okay? I want you to look into it and try to figure out yourself. We'll again discuss this next class.
We have our test next class.
Huh?
We have our test next.
You'll have your test back next class. When is the career fair? So you'll actually have time to attend the class, right? Because it's not going to.
It's not
We built this fucking stuff so that's impossible.
But in all day.
No, people have class, or we have lab.
It doesn't matter if it's on us. We're seniors.
It's not going to be here like.
But what if you get interviewed? But what if you get interviewed?
No, like, my.
That's just he just made like all the he doesn't need to go.
No, I'm just saying you can have class.
Excuse me, he had the job already, so that makes it the limit. But I know several of us are still searching,
So
so
class should be
So when do you want to move it? Friday?
Monday?
they're not gonna be here Friday.
Friday, where are you guys going?
Away.
Where are you guys going?
Can I come to your office?
Huh? When do you, career fair is 2 days.
No, it's Monday.
Why not Friday? Friday 2 to 3.
I have class, so that's why I'm not coming on Friday.
Can we have
And
Monday?
Mondays are better, I can come on Monday.
Monday is Friday 2 to 3 or Monday 2 to 3?
Monday.
Monday.
Okay.
Monday was I have Monday 11 to 5, so.
Alright, we'll do Monday 2 to 3. We'll talk whenever, or you can go through the lecture again.
I will come up Thursday.
You want to come on Thursday?
I'm doing all Thursday.
I don't want to do it twice for.
No, it's fine.
I get it.
If you want, I'll talk to you about it in the class in my office. So Monday 2 to 3, everybody. And when do you want your test back?
Today.
Huh?
You have to go to your office.